Good morning, everybody. Happy Monday. I apologize for being a little late today. I guess I was caught in traffic on the way to WebEx. So I guess 1 minute late is not the worst. Yep, good morning. So, yep, good morning. Yeah. So I guess for today, I'm just going to recap. Yeah, traffic is, especially at this time, traffic can be very bad. So it does make sense. So, okay, so for today, I'm going to just first go over the little error that I had in the selection sort that I sort of gave you guys. I fixed it on Canvas. I uploaded my new notes, but I want to just sort of go over one or two little things first, and then recap last time's content, and then just continue on with more content. So let's go ahead and begin the screen share and start. Okay, so I'm going to go to my assignment 1 notes. So this was the part that I sort of forgot to add. So I believe in my code, I actually did not use any for loop. I used only while loops, but this will be just as good. This part is what I sort of added into my notes afterwards, because you want to set I back to the beginning in order to resume or restart that outer loop and do that same work again. So what does this note here mean? So I did mention this, and then some students had a question or didn't understand what that meant. So I'm going to address both of these, or at least address this one right now. So let's go ahead and suppose we have a linked list. So, is everybody, is there some noise going on? I can definitely fix that. Okay, I will mute all. So, all right, so let's suppose we have the following linked list. I'm just going to just create a hypothetical list. There's no actual numbers, just a few entries in here, just so we can get an idea of what's going on. So I'll make it possibly 5-node list. And I'm just going to draw one arrow, but we know it's a two-way linked list. But just to keep it simple, I'll leave it like that. And then we'll have our I iterator set over here. And then J is going to be set actually to null. Okay, and one by one, we're going to traverse every node of this linked list. Just one by one, we're looking at this node, then this node, one by one. And we constantly compare the value in each node to our current max variable to see if this node contains a bigger value than what we saw earlier. So at some point, we sort of store the with this max POS, max position iterator, we store the node address that contains the biggest value. Then we swap it, and at the end what we do is we say, well, if j is nil, we set j to the end, because we want to swap. Let's suppose we found this is our biggest element, is at this index, let's say. So after we go through the whole entire list, because remember, once I equals j, it will stop looping in the inner loop, and then it will know which node was the biggest. It'll swap this node right here. Let's say this was my biggest value. It'll swap this with whatever's at the end. So after we're done with this, then at index j will contain my biggest value. So the biggest value will be stored here, because we will swap it to the end. Okay. And now what happens is, because what happens, I is going to move all the way to the end. We want to set I back to the beginning so we can do the same process again, except now what will happen is it'll loop I again from the beginning to the next node, then to the next node, and so forth. But at some point, I will equal j. So actually, before I move ahead with this, after we sort of swap to the end, j decrements by 1. So according to our for loop sort of counter, my mistake, j decrements by 1. So j is going to be over here. So right now, this is so far part of our sorted list because the max element was swapped to the end over there, and then according to how our code looks, j decrements sort of by 1 to the left after we do one iteration of the outer loop. So this is our max value, and j is now pointing to this node. So then I is going to iterate through the linked list once again to find the max. But what happens is, when I equals j, it'll stop, it'll end the loop right there. And the problem is that, so from I to j, you want to find the max, because we don't want to go beyond j, because after index j, that does not have to be looked at anymore, because any element after j is already in a sorted position. So what happens is, once I equals j, it will stop looping. But what if index j contains the max value? You have to do one more check to make sure that the value of I is larger than the max value, because maybe index j happens to be the max, a possibility. So in that case, you want to, store that maybe the max position might happen to be index j. And if that's the case, well then your swap nodes function can just not do anything, because if I1, or sorry, if IT1, IT2 point to the same node, then there's no swaps needed to be done. Just return out of the function immediately. So that's the issue. So what can happen is j keeps on decrementing by 1. So what will happen now is we're going to swap the biggest element seen from I to j into index j. So now what's going to happen is these two elements are now in their sorted position. And then j decrements by 1. Now I want to find the biggest element from I to j, but the while loop, once I equals j, will stop right away. But maybe index j happens to be the biggest element. Maybe not, but maybe. So that's why I have to do one more check after the while loop, just to make sure that, because what will happen is it will compare I to the first node, to this node. So it will find the max between these two nodes. That once I is going to point to that node, it will stop the loop right away. But maybe that element happens to be the max element. So I hope that sort of makes sense. That's why I have to do one more check after the while loop is over. And you want to set I back to the beginning, because I is moving by one node in the inner while loop. You want to set it back to the front to restart, but j gets closer to I, so we want to find the max in a smaller range of elements in our linked list. So that's that. Okay, so hopefully that clarified that. But anyway, the homework will be due on Friday, so plenty of time to work on. This is actually a bit of a heftier program because of the, I guess that swap nodes and linked lists are never really too much fun. So anyway, I'm going to post assignment 2. I'll cover it on Wednesday, just to not really overload us, since many of us might be working on this assignment still, but I will post assignment 2 on Wednesday. It should be an easier one. I mean, recursion can be a little bit challenging, but it's not going to be this, whale of an assignment like this one was. It's maybe a little bit tricky because recursion does have this sort of magic component to it. So anyway, let's go back to our notes from last week. So we have, we covered sort of big O notation last week, and basically what we're trying to do is we're trying to just see which functions belong in a set of O of n squared, and so forth. So last time I did a bunch of examples with this, and we concluded that O of n is an asymptotic class of linear functions. So O of n contains every linear function, so it's an asymptotic complexity class. It's a class of functions. So 5n, 6n, 20n, any linear function you can think of is going to be in this set O of n. Now, also I discussed a few more contents. I also covered what about n squared equals O of n. N squared has an asymptotic growth rate that's quadratic, not linear, so it cannot be contained within the set O of n. So no matter what, remember with using this big O definition, we can pick some big constant, for n over here on this side, but it doesn't matter because n squared, if n gets big enough, it will eventually pass any linear function because this number is very big for c. However, it's a constant, so it's not going to keep growing. N is growing, so this has a bigger factor. So that means this cannot contain the set O of n squared. Now, this statement right here is correct, but it's a very weak statement to make because it is correct, but we really, want to always try to lower this. So the function inside of big O, we want to make it as low as possible. That still encapsulates the function that we're trying to test that's in the set O of n. So in this case, root of n equals O of n is correct, but it's a very weak statement. This statement right here is a stronger statement. We want to always make sure that we always lower this function inside of big O, but it still encapsulates the function that we're trying to test for if it belongs in that set. So pretty much this question right here, if I say root of n equals O of n, that's sort of like saying, am I shorter than 1 mile? And the answer is, well, yeah. But it's not a very, it doesn't tell us if you're a tall or a short person. So you want to say, well, now this question is asking, am I shorter than 5'8"? Okay, so that kind of gives you a better idea of your height. So pretty much you want to always make sure that even though this statement is correct, you don't really want to say it. Same thing like this. I could also say 3n plus 24 minus 24 equals O of n squared. That would also be a correct statement to make. But it's also a weak statement because 3n minus 24 is linear. And yes, it does go in the set O of n squared because it's big O notation, which means that O of n squared contains every quadratic function, but also every function that has a smaller growth rate than quadratic is, so really that's correct, but this is a better statement to make. This is a stronger statement. To say this is a much better statement. But then if I go ahead and say something like 3n minus 24 equals O of root n, this is actually incorrect because there's no way a square root function can really encapsulate a linear growth rate. Linear has a bigger growth rate than this. So this little analysis on this. So now let's go ahead and list out several different classes of linear or classes of functions. So we have O of 1. O of 1 contains all the constant growth rates. So 1 is just constant. And what does constant mean? Well, constant means that the runtime does not depend on the size of the input n. So if n can be anything, doesn't matter, the runtime does not get affected by the input size. So we'll do examples of what that means, but it's not so challenging to understand that. Then we'll have O of, I'll just put O of log again for right now. Then we'll have O of n, then O of n times log n, or O of n log n, O of n squared, and I'll just sort of finish this up, be O of 2 to the power n. So these are a couple of different set of asymptotic complexity classes. So each of these are basically going to be set. So for the most part, in class, we're going to cover these different asymptotic complexity classes. So O of log n, well, we'll discuss that in a second here, but it contains logarithmic functions. O of n contains linear. O of n times log n contains functions that have the growth rate n times log n. O of n squared contains all the quadratic functions and so forth. So in this case, as we sort of go from left to right over here, we have a higher growth rate, as you can see. And that implies a slower algorithm. So the idea is that, well, if the growth rate gets larger, then the algorithm's runtime is slower. So think of these growth rates like time. So if you take an algorithm and it takes O of n squared time to finish, and another one takes n log n time to finish, then n log n was faster. The algorithm finished quicker. Because n squared means that it took n squared number of steps. So n will be your input size always. So n will always be the input. N squared means that it's quadratic number of steps with respect to the input size. N times log n has a lower sort of growth rate, which means that it finished a task in fewer number of steps, which means that n log n is faster than n squared. So smaller growth rate, that means we have a faster algorithm. A higher growth rate means a slower algorithm. Yes, because lower growth rate means that it took fewer steps to let me see. So it took fewer number of steps to finish the problem. Let's see something here for Q&A session. Yes, so everything, so basically O of n contains everything to the left. So for example, O of log n is also in the set O of n. O of n log n contains all these O of n functions and O of log n functions. O of n squared contains O of n log n, O of n, and O of log n. Yes. So that's that. Okay, so I think that kind of summarizes this part. So that's basically how you want to think about algorithms. We take our source code and we want to try to categorize it into which asymptotic class. And there's several of them. But these are the more common ones we're going to be using in this class for the most part. Now, one question is, what about O of log n? Let's look at this. O of log n. Well, you notice that there's no base right there. And we know that logarithms, you have to have a base. You can't just, have just log n. So what's the base of this logarithm? And, well, we can sort of say that, well, let's take a look. Let's try the following scenario. So maybe it's log base 2. Still nicer. So log 2 of n equals O of log n. Let's test this out and see if this actually is a correct statement. So, okay, I'm going to do the following. So I'm going to use log 2 of n less than equal to c times, I'm going to just pick any base. So I'm going to pick a champion. So I'm going to choose b as my base, my logarithm. And I remember from Algebra 2 back in high school, there's a formula you can use to convert the base of the logs. So if I say log 2 of n, I actually can convert this into log b of n over log b of 2. That's how you convert from log 2 to log b, I believe. So now we can see here, as long as c is larger than or equal to log b of 2, and n naught will make this, I guess, 1, this will always hold. Now, log b of 2 is just a constant. So that means that it's off by a constant factor. And in fact, if I would have chosen log 10 of n, it'd be the same idea. It would be log b of 10. If I chose natural log e, same idea. So between any two bases, so log a or log b, any two logarithms, they're off by a constant factor, which means that O of log n contains every logarithmic function. So every possible base. Natural log, log 10, log 2, all of them are instead log n because all of them are off by a constant factor. So between any two bases, log base A, log base B, I can convert one base to the other. And the factor would be some constant. Let's say if I chose log A of n, then it would be log B of n over log B of A, and B and A are both constants, so same idea. So that's just to sort of, clarify O of log n. So that's why when you see big O analysis, you don't see a base of the log because it doesn't matter. They're all the same. Asymptotically, they're all the same. Okay, so the next one I'm going to cover is going to be omega, which I'll just sort of briefly talk about this. So f of n, if it's in the set, omega g of n. So we're not going to be using omegas too much in this class, but I'll just talk about this a little bit. For this statement to be correct, f of n has to be greater than or equal to some constant times g of n, where the constant is bigger than 0, and n is bigger than n naught, which is bigger than 0. So it's the same idea as big O, except we flip the inequality symbol. That's all we had to do. So let's go ahead and I'm not going to really do an example. I'll just sort of very quickly sort of talk about this. So for example, is n equal to omega n? The answer is yes. If I go ahead and say, is n squared equal to omega n? This one is correct, but also for the same idea is that it's a very weak statement. So omega is like setting the bar low. So omega n squared is much bigger than n. So this statement is correct, but it's a very weak statement, just like when we had for if n equals O of n squared, that was also a weak statement as well. This is the same concept because it set the bar way too low. So that means we could have moved the bar a little higher and still gotten it correct. So if I say n squared equals omega n squared, this is also correct, but it's a better statement to make. But however, if I say n squared equals omega n cubed, this would not be correct. So same idea as before, I can pick a very small constant for c, so 1 over a very big number. Doesn't matter. N cubed will eventually pass n squared, which means that n cubed cannot properly lower bound n squared. So I'm not going to go through all the details, but the same idea like with the big O notation, we just set this up by picking a constant, picking n naught, and all these can be proven easily, but this one you can show that there is no way. I mean, for this one I'll just sort of show this, you can try the following here. Just say n squared less than or equal to constant times n cubed. I'll pick the constant to be a very small number. And n naught will just be 1. Doesn't matter how small the constant is, n cubed will eventually pass n squared. And then we have this problem. And then it's not going to be n squared is not going to be bigger than n cubed for all possible n's, from 1 to a very large value. So n will start from 1 and just grow to infinity or to a very big value, but n cubed will eventually pass any n squared function. So there's that. So this is going to be a lower bound measurement, so I'm not going to really discuss omegas too often. We're going to focus mostly on big O in this class, but just wanted to talk about that. Then the last one is going to be theta. So we have f of n equals theta of g of n. So in order for this to be correct, that means that f of n has to be O of g of n, and f of n has to be omega g of n. So if both of these are true, then f of n is equal to theta of g of n. So I'm not going to do any examples, but I'm not going to work these out, but I'll just sort of, explain these, just do a few quick examples. So if I say n equals theta of n, that would be correct. If I say n equals theta of n squared, that would not be correct. Because theta means it has to be exactly at that growth rate. It's not up to or at least, it has to be exactly n squared. Well, n is not exactly n squared. If I would have said n equals O of n squared, that would be correct. Not a very strong statement, but it would be valid to say that. But in this case, it's not valid because theta implies has to be exact. And same idea like this, that would also be incorrect. So theta, it means has to be very exact. Whereas big O means it has to be up to. It could be smaller, but can't be larger. Omega means it can be larger, it can be equal, but it can't be smaller. And theta is exact bound. So you can, of course, we can show easily, let's say n equals theta n squared. You can show that n does equal O of n squared, but it fails in the n equals omega n squared. It fails on that step, which means that because of that, it cannot be theta of n squared. So I'll just kind of breeze past this. I don't want to really spend too much time on that, but we're not going to really go over too much of this, but just sort of know big O and omega and theta. So I'm going to right now summarize these kind of in layman's terms. So we have the following. We have big O of g of n. I'll just sort of put this here. We have big omega of g of n. And then we have big theta of g of n. Now, before I go in any detail, I just want to just make this clear. I might have skipped this detail last week. So you noticed that in all these functions, so theta and big O, let me scroll way up for a second. I actually might have used like 3n minus 24 here, but notice inside the big O, I always just picked n squared. I didn't say O of 3n squared or O of 5n squared. I just said O of n squared. And the reason is because the constants don't matter. The constants are not going to make a big enough impact on these. Because n, remember, n squared is a very big, it's a growing function. So the constant and n, the constant has no real, it doesn't make an impact on the fact that n is going to get very large, so that constant plays no role. So we don't really use constants inside of big O. We just say n squared, which means that contains all the quadratic function. O of n, linear. You don't have to say O of 5n because that's silly, because O of n contains. So O of n contains the function 5n within it. So we don't have to use a constant here. So the functions we test to see if it belongs in that set could have constants and all that. But inside the big O, we always just do not include constants because they don't really play a role. It doesn't make the asymptotic growth rate different. So 5n or 10n, it's still linear. So we always use the most basic form of the function within the O notation. Just to highlight that before I move on here. Okay, so let's go ahead and just sort of define big O. And basically, big O is known as the upper bound. And omega is the lower bound. So pretty much n is the input size. And for when we do big O analysis or omega or theta, we assume that n will be the worst case scenario, the worst case input. So we have to always consider that because the worst case typically comes up, or not, maybe not the exact extreme worst case, but even average case is sort of an instance of the worst case. So n is going to be the input size or input that will guarantee some type of worst case behavior. So when I say O of g of n, that means in the worst case, we perform at most C times G of n number of steps. So at most is the key word here. You'll never do more than this. You could do less, but at most, C times G of n. It's upper bound. So worst case, at most, this many steps will be performed. For a lower bound, omega, so in the worst case, we perform at least C times G of n number of steps. And the key word here is at least. So I guess the one issue is a lot of students assume this incorrectly, think, oh, big O means worst case and omega means best case. No. So the worst case or the best case is really determined by the input. So n is the input, and input will be given in such a way that's going to produce a worst case scenario. So the idea is that in the worst case, no matter what, we always consider the worst case. Now, of course, we can consider best case input sometimes, but usually we care about the worst case scenario, because the worst case encapsulates every possible scenario. So if the worst case we have this many steps, well, then any other scenario has got to be better. So we want to always know what's the worst possible scenario we can have. So the input, we always analyze the worst case because that encapsulates every possible case. So the worst case is determined by the input. And then big O means in the worst case, we'll do at most this many steps. Omega means worst case, we do at least this many steps. We won't do fewer, but at least this many. So it's not really, omega is not best case and O is worst case. They're always worst case, but this is at most in the worst case. This is at least in the worst case. So hopefully that makes sense. And then the theta, well, it's going to be exact bound, which means that in the worst case, we perform, I guess, exactly C times G of n number of steps. Now, it doesn't have to be exactly. What I mean by exactly, it's asymptotically exactly, which means that if a G of n is linear, then we're going to exactly do linear amount of work. Whereas for big O, if it's O of n, the worst case, then there could be some input scenarios that could be better than, O of n. They'll never be worse than O of n. So when I say, at most, I'm talking about really asymptotically, at least, not by a constant. So I say exactly for this one, I mean asymptotically exactly, not, doesn't have to be exactly the same function. But theta of n, remember, means all linear functions, but only linear function. It doesn't contain the log functions in theta of n. So I think this is really the most important details, is understanding, what these mean. This is really kind of like the real heart of the problem. So the rest is all math, which can be very easily, anybody can show that math, but to understand what that math means is more important. This is what they mean. So that's pretty much that. So now let's go over some more sort of analysis of sort of how to determine different function growth rates. So using this big O and omega sort of definitions is good enough, but there is a nicer way you can actually use to determine which function has a bigger or smaller growth rate. This will be L'Hopital's rule. Let's go ahead and discuss L'Hopital's rule next. So let's see. Sounds like a French name. L'Hopital's rule. It's a very nice mechanical way to be able to determine which function has the bigger or smaller or equal growth rate. So here's how the rule is set up. And just a warning, I'm going to first do the following. I'm going to do the following first. Yeah, I know we have limits, we have calculus again, but don't worry, the calculus stuff will not be too bad in this class. Someone left as soon as I put limits right there. Yeah, I understand. But I mean, so okay, here we go. So I took calculus in high school. So I haven't done actual formal calculus like in about 15 or so years. Yeah, so it's been a while for me. So I don't remember everything from calculus. That's how we can show that I'm not going to get too insane with the calculus stuff because I don't remember everything from it. And I don't want to learn it now because I have a lot of other things I have to constantly learn. So I don't have time to learn all this calculus nonsense. But anyway, we have two functions, f of n and g of n. I want to see which one has the bigger growth rate or if they're equal to each other. So L'Hopital's rule will give us a ratio. So we're going to get three possible results. Either we're going to get 0 for our result, or infinity, or we're going to get some constant that's larger than 0. We have three scenarios. If 0 comes up, that means g of n is larger than f of n. And I mean larger, asymptotically larger. That means g of n was n squared, f of n was n. So g of n is asymptotically larger. Infinity means that f of n is larger, is larger than g of n. If it's a constant, then f of n and g of n grow at the same rate. So that constant tells you the factor it's off by, the constant factor it's off by. So they have the same growth rate, but it's off by some constant factor, which really, it implies they have the same growth rate. So that's how we can use this method of being able to determine which function has the bigger or smaller growth rate. So let's go ahead and do some testing on this. Let's test out a few examples. So what about f of n equals 3n minus, actually I'm going to use maybe n squared. So you have 40n squared minus 30n plus 22. And g of n is going to be 55 n root n plus 20,000 n minus 3. Hopefully I didn't get myself into trouble here with this. Infinity. I see a question. I'm not sure what that refers to, but we have this limit. Is this about how calculus can be scary, or is this just... Yes, this ratio could actually diverge to infinity. Yes, it's infinity right there. So that means that, yes, so this ratio could diverge, or could converge or could diverge. So we'll see. Well, when I see an example right now that's going to probably cause this. So right now I'm going to test these two functions out. Now we can probably see right now f of n is going to be larger, but we have to, show this. So let's go ahead and use a limit definition as n goes to infinity. So the input will never be infinity. but we're going to assume n will be very large. So infinity means it's going to grow to some very big value. So we're going to assume infinity, but the input size will always be some value, but the n can be variable length. So that's why infinity means it just becomes very large like that. So I'm going to try the following out. So 40n squared minus 30n plus 22 over 55 and root n plus 20,000 n minus 3. Okay, well, let's do this. So we're going to set n to infinity. So we get infinity over infinity, which will give us 1, right? Easy. I mean, calculus would have been so much easier if that would have been the case. But unfortunately, remember from calculus that not all infinities grow the same rate. So infinity over infinity is not going to be 1, unfortunately. So we have to do a little bit of algebra to sort of figure this out. So I'm going to actually factor sort of a few things out. I'm going to factor n squared out from our numerator to get the following. Like that. Then I'm going to factor n, in this case, out. 55 root n, actually. Oops, oh, okay. So I'm going to actually, maybe I have to factor out more than that. Hold on. So I'm going to say n root n, I'm going to factor out over here. We go to 55 plus 20,000 over root of n minus 3 over n root n. Alrighty, so I factor these out. What's going to happen is that, well, this is going to remain, let's see, I think it's going to be root n right there at the very top. So now we have root n. So you have 40 minus 30 over n plus 22 over n squared over 55 plus 20,000 over root n minus 3 over n root n. So basically now we can set n to infinity, and we know that these are going to just become 0 because a constant over infinity is going to be just 0. So we end up getting root n over 55. This is going to converge to infinity. Or sorry, no, diverge to infinity. Like that. So we end up getting infinity, which means that the function on top had the bigger growth rate than the function at the bottom. So, another way we can kind of also estimate this is that we have 40n squared minus 30n plus 22. That's a quadratic function. And we also can think of it as the most dominant term is going to take over the entire function's growth rate. So 40n squared minus 30n is still going to be, it's going to be O of n squared. Now, it doesn't matter how big this n value is. It could be 5 million n. It's still going to be n squared in growth rate. So a few kind of ways to guesstimate this faster is we always eliminate constants, and the bigger growth rate term has the dominant sort of growth rate, which means that takes over the whole function overall. So it's kind of like saying 40n squared is like having $1 billion and subtracted by 1,000. Well, you're still a billionaire because 40n squared is very big, like 1 billion, and 30n is very small, like 1,000, which is 1,000 is a lot of money, but compared to 1 billion, it's not going to work out. Now these cancel out because I set n to infinity, so this constant over infinity becomes 0. And then we have, and then these become 0, so 55 plus, zeros right there. And then we have root n at the very top like that, which this will actually grow to infinity at the end. So infinity over a constant becomes infinity. We're able to conclude a solution like that. So yeah, so basically we can kind of guesstimate this easier because we have n squared and we have n root n. N squared is bigger than n root n, so we already can conclude that this is going to diverge to infinity, but just, you know, just to estimate this. So let's do another example, I guess. Try this example here. Limit as n approaches infinity. I'll pick, let's say, 4n minus 55,000 over 10n plus 22. So we can see right now they're both linear growth rates because remember 4n minus a big amount. Yes, that's the answer to the question right there. Yep. So in this case, we see that it's going to be definitely linear over linear, so it should converge to some constant. And remember, 4n is much bigger than any constant. So it doesn't matter if we're subtracting by 55,000, 4n is much bigger. It's like having a billion minus 1,000. 1,000 is a lot, but compared to a billion, it does not really play a big role, unless you're that crazy guy from Silicon Valley who has to have 3 commas next to his name. But if you're not a psychopath, then a billion minus 1,000, you're still a billionaire. I mean, you're closer to a billion than I would be, of course. So, you know, there's that. But anyway, let's go ahead and work this one out now. So I'm going to factor the n out. So you get 4 minus 55,000 over n over 10 plus 22 over n. So we can cancel these n's out. 4 minus 55,000 over n over 10 plus 22 over n. So now we can set n to infinity, which will give us, these two will be 0 and 0. So you have 4 over 10 is our result, which will be a constant that is in fact bigger than 0, which means that these two functions have the same asymptotic growth rate. So L'Hopital's rule can be nice in certain situations. Now, of course, you can guesstimate this. So for a test question or a homework question, we have to sort of group functions by growth rate or sort them by growth rate. You can probably just guesstimate most of these because you can see that these are both linear, so they're the same. This one is quadratic, this one's n root n's, this one's bigger. So you could actually guesstimate that, but this is just a way to sort of, you know, more mechanically show you which one is bigger or smaller. So let's do one more example, which is going to be a little bit tougher, I suppose. So what about the following? So let's ask ourselves the following question. Is root of n equal to O of log n? So this question is asking that is root of n, does it have the same growth rate like a log n or smaller or not? And yes, we can use derivatives of L'Hopital's rules. So we're going to show an example really soon. So up to this point, we didn't really need to. We could use simple algebra to do this work, but we can do derivatives, of course, to use L'Hopital's rule. So in this case right here, is this a correct statement? So is log n equal to or larger growth rate than root of n? Well, let's see. So it's not, you know, so using the standard big O definition is not very clear. So if I try to say something like, okay, root of n less or equal to c times log a of n, well, I mean, it's not really obvious. I mean, like, you know, it's not obvious really, which if it is going to work for some constant. So L'Hopital's rule is going to be more useful right now. So I'm going to actually apply that right here on this scenario, on this particular instance. So n goes to infinity, and we're going to have root of n over, now I have O of log n. So that means I can choose any logarithm I want, any base I want. So for some reason, I'm going to go ahead and choose natural log as my champion. And the reason why I can do this is because, remember, every log is off by constant factors. So it doesn't matter which one I choose. It's not going to affect the ratio by L'Hopital's rule. So I can pick any log, and I'm going to choose log of n, or natural log of n, sorry, because I'm going to apply derivative on this, and natural log derivative is very nicely defined. So why make this problem harder? So right here, we have to do a derivative of the f of n and g of n separately and put them back together and then see if we can find a ratio. Because right now, once again, this will give us infinity over infinity, which is not going to give us a conclusive answer. So m to the 1/2 derivative would be 1/2 n to the negative 1/2. So this is going to give us a derivative of 1 over 2 root n is a result, infinite derivative of root of n. And natural log of n derivative is 1 over n. Okay, well, we have to multiply by the reciprocal. So we end up getting n over 2 root n. This will factor out to be root n over 2. And this amount will diverge to infinity. Which means that square root of n has a larger asymptotic growth rate with any logarithmic function. Therefore, this is not correct. However, if I would say is O of log n in the set O of root n, that would be correct. This is saying that is every log function in the set O of root n? And the answer is yes, because root of n has a larger growth rate than natural log of n, which means that root of n has a larger growth rate than any logarithmic function, because since all of the log functions are off by a constant factor, that means root of n is larger than any any logarithmic function. So sometimes the derivative can also be useful to solve this problem. So just know this. So I'm not going to have you, prove this, or maybe, for an assignment, you'd have to sort of work these out if you're not convinced, or if you want to just double check or make sure you don't, guess incorrectly. But of course, you can do this. So, all right. So that's sort of L'Hopital's rule. And because infinity was the result, it's a bigger growth rate function, which means that this can't be correct. So you can actually determine, so let's say, let me go back up to my notes for a second here. So if it's a constant, that means f of n and g of n, so then f of n equals theta of g of n in this case. They have the same growth rate. If it's infinity, then g of n equals O of f of n, because f of n is larger than g of n. If the result is 0, that implies f of n equals O of g of n. Let me put this here just as a note, so we can sort of make the assumption. So f of n is O of g of n. In this case, g of n is O of f of n. In this case, f of n equals theta of g of n, because they have the same growth rate. So based on the results, L'Hopital's rule, we can conclude these statements. Because since g of n is the larger growth rate, then f of n must be in the set O of g of n. So just to add on to those notes right there. Oh, my mistake. F of n. No, sorry, no, g of n. F of n. Thank you for correcting that. So that's how you want to think of that. That would have been too obvious of a statement if it was just that. So That's the result. So based on L'Hopital's rule, you can conclude, these statements right there. So that's basically sort of the math kind of analysis for now, at least, with algorithms. So the whole concept is that we're going to have program code, and we want to be able to determine what's the number of steps that this code produces and be able to classify it into an asymptotic complexity class. So we first start off with just asymptotic complexity classes and how to take functions and group them into classes using L'Hopital's rule or definition of big O and whatnot. So now let's go over actual code snippets and try to classify them into a big O class. So I'm going to go ahead and create a new page. Let's go ahead and talk about this. So now you want to look at C++ code and be able to count the number of steps produced by it. So I have my handy notes here because otherwise I'm going to skip certain steps potentially. So let's go ahead and start with a very simple example. Going back to our classic for loops, which should not need any introduction to this. We know how these work. And what would any CS class be without the infamous hello world? Yeah, somehow I was able to sneak it into 302 as well. Somehow it just sneaks in there when you do any kind of CS content. So hello world. So for these code snippets, n is going to not really be, we can think of n really as not the base 10 representation of number. It's going to be the size of the input. So if the input is 10, n is going to be 10 ones. So n is thought of as not really a base 10 number, but rather a size of the input. Otherwise, all of these will be exponential runtime. So this n is not a base 10, but it's a size. So these cout statements right here, this cout statement is going to be O of 1. So every single statement in C++ can be thought of as a constant runtime. Now maybe it's not really constant, it does a lot of work behind the scenes, but in terms of us writing code, we can't really code-wise improve this cout hello world. It's going to do that based on the hardware. So also, if n gets larger, then outputting hello world, just that string hello world, is not going to take more time. It might do it more number of times, but that cout hello world is not going to take more time if n is larger. So that's why it's constant in runtime. So let's try to see what's the number of steps over here. Well, if I were to do this, we would have this summation I equals 0 up to n minus 1 O of 1. Yes, we have summations also in this class. So basically, we can think of it as we're just doing a summation phi equals 0 to n minus 1, and we'll just use 1. So O of 1, we can just substitute it with 1, because that means 1 is the simplest constant. So here, we're going to add 1 from 0 to n minus 1, which will actually involve us to do n number of additions. So we're going to add 1 n number of times. This will give us the result of n, which means it's going to be O of n. So this piece of code has a runtime of O of n. Really simple, because we're doing this constant amount of work, which is cout hello world is a constant operation, and we're counting how many times we're going to cout hello world, where we're going to cout hello world n number of times. If n was 10, it would output hello world 10 times. If n was 20, outputs 20 times, and so forth. So that's that. So, okay, so a nested loop, we can kind of, estimate it to be n squared. For the most part, you can do that. There are instances you have to be careful with that, but usually, yes, if you have a nested loop, then you can just sort of just say n squared because you can multiply n times n like that. But I'll do a more mechanical way of showing that because there are certain cases that doing that assumption can cause an issue. But I think for the most part it doesn't, but there's one scenario where it can be a little bit tricky, but usually, yes, you can definitely do that. Let's do another example. Int I equals 0, I less than n once again, I equals I plus 2, and then we'll put our fancy hello world here. Sure. So, the runtime for this one. Well, let's figure this out. Again, we're going to do a summation. I equals 0 to n minus 1, and the whole thing divided by 2. Because we're adding by 2 this time, so we're going to do half as many amounts. We're going to output hello world half as many times in this situation. So we're going to get n over 2 as a result, which will also be O of n. Not too fancy. So the idea here is as long as we're adding by some constant, this will always be O of n. So if I added I by 10 or by 20 or by 100, it would still be O of n, because n over 100 is also O of n, because that constant of 100 is very small compared to how large n is. So it's like n divided by 100 is like a billion, and you take away a little bit from a billion, it's still relatively a billion. So that's the idea. So I think that sort of covers these two examples. So it's really, these ones aren't too bad. Let's go ahead and now discuss some other ones here. Okay, I'll do this one. Another not too challenging one. For int I equals 0, I less than n times n, I plus plus, and of course we have our infamous hello world. Like that. So once again, you want to have a summation so we can see the number of steps here. So again, the hello world will be a constant operation. I'll use blue to do this to be consistent. So we have I equals 0 up to n squared minus 1. So we're going to add 1 n squared number of times to give us O of n squared. So there's that. Now let's go over this example. Let's try the next one. This one, so far, these are pretty kind of elementary, but let's go ahead and now go over the following scenario. For int I equals n, I greater than 0, I equals I divided by 2. This one's not so obvious, or at least doesn't seem so obvious. And again, we gotta go with our infamous hello world, like that. Okay, well, we're dividing by 2 every single time until I equals 0. So what's the number of steps over here? Well, this particular sort of code snippet has a very defined behavior. So if I take a number n and I keep dividing it by 2, and I count how many times I divide it by 2, no, this shouldn't be infinite loop, because it starts from n, so this should not be infinite loop, I don't think. Doesn't seem like it should be. at some point I will become 0, because remember, at some point I will become 1. 1 divided by 2 will be integer 0, which will force this comparison check to be false, and it will escape the loop. So, yep. Yeah, no problem. So, let me see. So in this case, if I divide n by 2 and keep dividing it by 2 again and again and again, I count how many times I have to divide n by 2, then this is going to be a logarithmic sort of growth rate. So definition of log really is, so log 2 of n really means that if I divide n by 2, how many times I've divided by 2 until I get 1 or 0. Even for log 10 of a number. So if I take log 10 of n, that means how many times do I divide n by 10 until I get 1 or 0. So this is definition of logs. So it's O of log n only because it's just definition. Definition of logarithms, basically. That's what a logarithm growth rate is, divided by 2 until we hit 1 or 0. So that works. Even 8, log 2 of 8 is 3, because 8 divided by 2 is 4, divided by 2 is 2, divided by 2. So it'll take us 3 divisions by 2 to get 1 or 0. So that's what the definition of logs really is. So it's going to be log of n. Now what about this example? And of course, our infamous hello world. We can't not include that anymore. So once again, we're dividing it by 2. So we see this updater in this sort of way, which really implies logarithms again, because dividing by 2 is going to be logarithmic. So in this case, we have n squared. So we're going to get log base 2 of n squared, which will just be 2 times log 2 of n, which is just O of log n as well. Remember this logarithmic sort of property. If you have log up to n up to some power, we can bring the power to the front like that. Let's say log definition. So if it was n cubed, n to the 5th power, or whatever, log 2 of that is going to bring the exponent part to the front, and they're all going to be logarithmic. So it's kind of neat. So it's just, to kind of be careful with this. I could have it could be n to the 4th power over here for I. It would still be O of log n. Now, on the exam, I'll definitely have a question like this. I'll give you a bunch of code snippets, and you have to sort of give me the result. Now, you have to give me the asymptotic sort of complexity. Now, technically, all of these really are theta, because this is going to be exactly, so let's look at this question. Let's look at this one for a second. This is not going to end early, ever. So it's going to always end after n squared number of steps. So in reality, these code snippets really are actually theta of n squared. So I might use on the exam theta, not big O, only because of the following. So let's say you have a multiple choice answer like this. Let's say you have A would be O of n squared, and B would be O of n cubed, let's say. Let's say you had something like this. Let's say you circle this answer. And a system would mark it wrong, as it should kind of mark it wrong, but technically it would be correct. So for that reason, I might use thetas on the exam, so that way you cannot, try to get any points like that and say, well, technically, isn't it O of n cubed as well? Like, yeah, technically it is, but it's sort of like, okay, fine, this would have been correct as well. If I would say O of 2 to the power n, that would also be correct, but that's kind of a bad statement. So that's why on the exam I'm going to use thetas, so that way only one of these can be correct, because if I circle C, or I circle B actually, this would not be correct anymore because it's not theta. It's O of n cubed, but it's not theta of n cubed, so only one of these can be correct. So just to let you know. And also, I can variate these questions as well any way I want. So I also, if I wanted to, I could have done this. I could have had I equals n times n, I greater than 0. I could have had I minus minus. That would have been still correct. This is still n squared. We're starting from n squared, working our way down to 0, but it's still going to run n squared number of times. And likewise, I could also, let's go up here for a second, I also could go I equals n, I greater than 0, I minus minus. That would also be n. So either one of these would be correct. So I could do this on the exam just so it won't be the exact same problems like I will cover in class. And also, for the log functions, I could have I equals 1, I less than n, I equals I times 2, the same idea. It's going to be log of n. So if we start from n and work our way to 0, or start from 1 and work our way up to n, at this rate, it's going to still be logarithmic. So I could, of course, mess with these a little bit. So it's not going to be the exact same question like, let's here on the notes, but it's very much, the test questions on these are very much based on what I'll cover in class. Just maybe I'll modify them a little bit so you can't just do a pattern match and get the correct answer based on that. So anyway, I think we're almost at time. So I'm going to end it right here. So homework is due on Friday. I already updated this on Canvas, I believe. So I guess stay safe. Take care, you guys. Thanks for watching. And I will see you guys next time.